So I was talking about Coulomb's law. Coulomb's law, I think, is pretty straightforward. Given two charges, say Q1 and Q2, not really concerned about the SIGN of the charge right now. Coulomb's law says that, well, there's some force between these two charges based on their separation distance and the magnitude of the charges. So call that separation distance R. Then the force magnitude is equal to K, Q1, I'll put it in absolute value bars, K Q1 Q2 over R squared. So this is an inverse square law. All right, there are lots of inverse square laws in physics or nature. Things go like the square of the distance between them. That's due to the Euclidean space that we live in. Just like the distance between 2 points, you take the sum of the squares, take the square root, and you get the distance between it. So it's an inverse square law. Now, K is called Coulomb's constant. You may see it with a little sub E or sub C or something, but I just write K because I know the context. We're talking about Coulomb's law. So K is equal to 9 times 10 to the 9 Newton meters squared per Coulomb squared. It is a combination, K, the Coulomb constant, is a combination of 4 pi and the permittivity of free space, which is a more fundamental unit, epsilon naught. Epsilon naught is equal to 8.854 times 10 to the negative 12 Coulomb squared per Newton meter squared, okay? And in a lot of text, they won't even use K. They'll just use 1 over 4 pi epsilon naught. Okay, so K is equal to 1 over 4 pi epsilon naught. All right. Now, depending on the SIGN of the charge, what I said was when I work these problems, I'm going to draw in the vectors and I'll deal with the direction of the forces by just looking at the picture, okay? So if you have a negative and a negative here, maybe this is a negative Q1 and a negative Q2, then these two repel one another. Okay, there's a force pair, F1 and F2. They're the same magnitude, they're opposite directions. That's always going to be the case for point charges, Coulomb's law. That force pair is going to be equal magnitude and opposite direction. It's either going to be away from the two charges or toward the two charges, okay? Okay, so I posed this problem of two charges on a line. So let's say you have a negative 5 microcoulomb charge and a plus 1 microcoulomb charge. And they're on some line. They're fixed. Don't know how they're fixed, but they're fixed. Okay. So the question is there a place along that line that I can place, that I can put a positive charge? Let's say it's a positive Q, okay? So another little positive charge. Is there a place along that line that I can place this positive charge such that there's no net force on that positive bit of charge? Well, you might say, well, what about in between somewhere? Well, if we look in between, and this is a positive charge, You get F1 in this direction. I'm calling that the force due to 1. And then F5 is in this direction as well. Yeah? Because likes repel, opposites attract. There's no place in between that I could put this positive charge and get the forces to cancel. Yes?
Can you put on the right?
I'm getting there. Yes. The answer is yes. Okay? I'll leave that for the last place.
Shouldn't negative.
Okay, this is a positive charge.
So what's going this way?
Nothing. These two charges are fixed.
And they're opposite, so they should attract.
I am not concerned about the force on these charges. I'm looking at the force on plus Q, which I just put there.
So you just wanted to like pull in both directions?
Say that
You
again.
just wanted to pull in both directions?
Yeah, they're both in the same direction. The force is because you get a repulsion from this one and you get it being attracted to this one. Okay? You might say, well, what about over here? Okay, F1 is in this direction. F5 is in this direction. Okay. They're in opposite directions, but what's the problem with placing it over there on the left? Yeah, the 5 is always going to win, right? It's larger and it's closer. There's no way you're going to cancel that F5 with F1. You've got a smaller charge and it's farther away. Okay? However, like David pointed out, if we place it over here, okay, then F5 is in this direction. Oops. Not very good. And I'm going over here to the end of the board again, but. Okay, F5 is in that direction and F1 is in that direction. And you can find a spot there where you can sort of tune it or find a sweet spot where F5 is equal to F1 in magnitude. And that's what you're looking for. Okay? Let's see how to find that place. So I'm going to make this simple as far as the distance between these two. 1.0 meters. Right. So the distance between those two fixed charges is a meter. I'm going to call this distance. I could choose the origin anywhere I please, but I'm going to call this distance x. So I'm making this is a one-dimensional problem. I'm making this the origin, okay? What I want is already know I got the vectors in the correct direction and I'm out over at the correct place. I want F5 equal to F1 by adjusting x. So let me write down the magnitude for F5. So F5 is equal to K, Q. Q is just some arbitrary positive charge, times 5 times 10 to the negative 6 coulombs, divided by 1 meter plus x quantity squared, right? Because the negative 5 is 1 meter away plus x. F1 magnitude. F1 is equal to kq, 1 times 10 to the negative 6 coulombs, divided by x squared. Set those two equal to one another. Solve for x. K. KQ. 5 times 10 to the negative 6 coulombs divided by 1.0 meter plus x squared is equal to KQ. 1 times 10 to the negative 6 coulombs divided by x squared. Well, we get some nice cancellation. That goes away, that goes away, that goes away, that goes away. Okay. All that stuff goes away, and you get 5 over 1 plus x squared is equal to 1 over x squared. How do we solve rational equations like this? Cross multiply. Turn it into a polynomial. Okay? So 5x squared is equal to x squared plus 2x plus 1. Okay. All right. So you get 4x squared minus 2x minus 1 is equal to 0. Solve. Okay. How do you solve it? Plug it into your calculator or whatever you need to do. Can somebody please do that now? So you get 2 plus or minus the square root of 4 plus 16 all over 8, if I'm looking at it correctly. So this is equal to 1 plus or minus the square root of 5 over 4, I think.
I got negative 0.3, 0.9,
Okay, x is equal to negative 0.31, 0 point what? 81, and that is in meters. Okay. All right. This answer is true if those charges were both positive or if they were both negative. You could find a place in here if they were both positive or they were both negative. You could find that place in here that would give you cancellation. Okay? But that negative answer does not make sense for the physics. Okay? That's it. So out here at x equals, so this is not to scale, x equals 0.81 meters, that's where you get no net force on Q. Okay. Are there any questions on that? And obviously you can check it if you want to, but. Questions on that? Okay. All right. So I want to talk about a new concept, something really truly is new for us, that we'll use over and over and over and over again as we go along. And this is the idea of the electric field. Okay. The electric field. So fields are, we talk about either gravitational field, the electric field, the magnetic field. It is not just some sort of construct that helps us solve these problems. The electric field is something that is a real, measurable quantity that exists, just like the gravitational field, okay? The gravitational field in this room, we can measure, I'll talk about that in a second, and it is a physical quantity that we think of as existing in space. All these things that, when you get to upper level physics, all these things are, many things are based on this idea of a field. And it's not just an idea, it's a physical entity, okay? So let's think about the gravitational field, even though we didn't talk too much, if any, about it, but I think you can formulate an idea, okay? Here's Newton's law of universal gravitation. Okay, it's an inverse square law just like Coulomb's law. Big G is a physical constant that makes this work out in newtons. This has units of mass, it has mass. It's kilograms, meters squared, okay, all that stuff. So, if you want to figure out the force acting on you due to gravity in this room, okay, then, well, Earth is providing most of that force, according to Newton's law of universal gravitation. If you know the distance you are from the center of the Earth, the mass of the Earth, your mass, and this constant, you can figure out the force on you due to gravity. And it's going to be pretty close to, really close, so I'll put a little m, your mass, times the acceleration due to gravity, right? Which we all know that the acceleration due to gravity is about 9.8 meters per second squared, all right? But if you really wanted to be super careful and you want to calculate the force due to gravity on you very correctly and very accurately, okay, then not only do you have to know exactly the distance you are from the center of the Earth, you got to know how far you are from the sun. Because the sun at this moment is providing a force on you due to gravity. So is Jupiter. So is the moon. So are all these other objects, okay? The moon is pretty significant. I mean, you know, the moon moves the tides around. It makes the tides go in and out. Anyway, so that force on you due to gravity is changing, and you have to know at some instant, all right, where all these objects are and the distance. This is called action at a distance, okay? You got to know something about all those things that are acting on you out in space. However, with this idea of a field, we make it a local quantity. What I could do is I could take a little test mass m naught. This is I'll call it a test mass. Okay. And move it around, and if I have a really, really, really accurate scale to measure the force, I can move this little test mass around in the room, and I can calculate the force on that little test mass everywhere in the room. So I can map out that force for the room. Okay? And G as a vector becomes F over m naught. Okay? Why do I have this little test mass? The little test mass is there to, well, obviously to measure the force, but it's not large enough to really perturb the field very much. It's a very, very tiny little mass. Okay? Yeah.
What do you mean by perturb?
Change. Perturbations mean small changes. If you're perturbed, somebody hasn't really upset you really badly, they've just sort of made you a little bit upset. Okay, perturb. All right. Perturbations. Perturbations in physics mean little small changes. Okay? Like if you have initial conditions for a differential equation and you perturb those initial conditions, that means you change them by some little delta or epsilon. You with me?
Yes, sir.
Okay. So this little test mass isn't enough to perturb the field very much. Okay. So then I get a field based on all these little measurements that I did. And if I want to know the force on a particular object in that field, I just multiply G times M, and that's what we do. I multiplied my mass times the field that I just measured, mg. That turns that action at a distance. I don't need to know where Saturn is and the sun and all those things. That turns that action at a distance into a local property. Okay? But truly it is local. It is local. Your acceleration at this point, the force on you due to gravity is due to the gravitational field in this room. Okay, and that field may change, but all right. So here's the idea. We're going to do the same thing I talked about with the little test mass, but we'll have a test charge. So here is a positive bit of charge Q. All right. I want to find out what the electric field is due to this charge Q. Well, what you do is you take a little test charge, Q naught. Maybe it's a proton. It's a little tiny bit of charge. And you move it around and you look at the force on it. We know from Coulomb's law that force, and these test charges, we always make them positive just by convention. Okay? There's a force in that direction. Down here, I move Q naught down here. There's a force in this direction. Put Q naught up here, there's a force in this direction. Now I'm drawing all these force vectors, they're not to scale, okay? I'm just getting an idea of the direction of the force. We define the electric field just like I was talking about with the gravitational field. We define the electric field for a point charge as F divided by Q naught. Okay. The electric field is a vector, just like any other old vector that you would encounter. It's a vector. It has units of newtons per coulomb. It's an amount of force per coulomb of charge. Okay? Now, for a positive charge, so this gives us a picture sort of what that field is going to look like. And I'll get a little more technical here in a second. So for a positive bit of charge, Q, the electric field lines start on the positive charge and they radiate all the way out to infinity. So I told you we'd be drawing these silly little pictures to help us understand this stuff. Okay, so these lines that I drew are the field lines. The density of the field lines, meaning sort of lines per section, that represents the magnitude of the electric field. The direction, obviously, I hope, represents the direction of the field. So the lines are very dense near the charge, and then they get more and more spread out as you get farther and farther away from the charge. Okay? So for a point charge, this is the electric field due to a point charge. I know that it's F over Q naught. F is equal to, in magnitude, F is equal to K. Q naught over R squared, right? By what we've been doing with Coulomb's law. So E as a vector, and it is a vector, is equal to K Q over R squared R hat. R hat is that little radial vector. It's that vector that points radially outward, and it defines the direction of the radius or the radial component, okay, in polar coordinates. So you do have to pay attention, that's a really long Q. You do have to pay attention to the sign of the charge, because a negative charge will have field lines that point in the opposite direction of R hat. Positive charges have field lines that point in the direction of R hat. So for a negative charge, the field lines start out at infinity and they end on the negative charge. Okay. How many do I need? I don't know. Many as I can fit in there, I guess. Okay. All right. The electric field always begins on positive charges and it ends on negative charges. So, let's say I have a collection of charge like this. Here's a positive Q and a negative Q. Take the little test charge and I map out the electric field in this region. The electric field is going to look something like this. All right. The field lines will begin on the positive and end on the negative. They're everywhere in space. Okay. All right. That's the best I can do. You can find this picture on the internet. Okay. The density of the lines represents the strength of the field. The direction gives you the direction, okay? So if I place a charge in this field, some arbitrary charge Q, then the force on that charge is going to be along or tangent to that field line. If it's a negative charge, it's going to be in the opposite direction. Okay? So this is, I want to put this in a box. Right, that's what we're going to be using over and over again. So you can turn this around. If you know the field, then the force is equal to QE. That's what we're after. We get an expression for the electric field in some region, and then we can place any old charge we want to in that electric field and calculate the force. Okay? Just like if I can write an expression for the gravitational field in this room, then I can place any old mass I want to in this room and calculate the gravitational force. All right? At first, when we start doing that, this idea of a field, the first sort of problems we're going to do, it's not much different than what we did with Coulomb's law, okay? It's still sort of action at a distance, but we're going to get to the point where we can calculate the electric field due to continuous objects like a sphere of charge, a line of charge, a disk of charge. Okay, and we can get expressions for the electric field in the region of a sphere of charge or a disk or a ring or a line. Okay, and that's useful, all right? So, let me say a couple other things about the field. This may be obvious, maybe not, but it is definitely summable. You add it up. It's a vector. You add it as a vector. So the electric field for a collection of charge is simply K times the sum from I equals 1 to N, depending on the number of charges, of Q sub I over R sub I squared times R sub I hat. Okay? Let me draw a picture of that. So here's Q1, here is Q2, and maybe over here is Q3. And I'm out here at some point. This is not a charge. This is some point in space P. Okay? And the question is, what is the electric field at P? What is E? It's a vector at P. Okay. Sum it up. Okay. These little radial vectors point from the charge to the point of interest. Okay, they can move around anywhere you need them. Try to get it straight. There's R2 hat, and there's R3 hat. Okay? Here's the distance R1. Here's the distance R2, and okay, my lines look halfway decent today. Okay, here's R3. R3 is not so great, but it's supposed to be a line. Looks more like a curve, but okay. Those are the distances. So if Q1 is negative, then you get an electric field vector that's in the opposite direction of R1 hat. If Q2 is negative, it would be that way. If it's positive, it's that way, and so forth, okay? Let's add them up. So you just add them up. E at P is equal to K, Q1 over R1 squared R1 hat plus K Q2 over over R2 squared R2 hat plus K Q3 over R3 squared R3 hat. All of these little vectors, these unit vectors, are there to remind you that this is a vector sum. You can't just add it up. You got to do the vector thing. You got to, okay? All right, let's look at an example based on this idea of summability. Here's a square. Let's say that it's 50 centimeters on a side. Okay. And there are 3 point charges that are fixed at the corners, 3 of the corners of the square. Up here there's a -1, no, I want a positive. +1 microcoulomb. Here's a -3 microcoulomb. And over here, I'll use odd numbers. I like odd numbers. I don't like even numbers. Okay. Well, yeah, I like odd numbers. Okay, they're more interesting. All the primes are odd, so. Okay. I'm up here at some point. There's no charge at this point. I'm going to call this point P. What is E at P? Same question I had over here. Well, you add it up. First thing I'm going to do, though, since I've got the picture drawn, is I'm going to draw in the vectors, the electric field vectors. I know that for positive charges, the electric field points away from the positive charge, and for negative charges, the electric field points toward the charge. So, this would be E1, not to scale necessarily. This would be E3. Getting the directions down, and this would be E5, okay? Because 1 and 5 are positive, so those field vectors are pointing away from 1 and 5. 3 is a negative charge, so that vector is pointing toward the negative charge. You guys keeping up with all of this? Notation, notation, notation. Okay. All right. Sum them up. The first thing is I'm going to calculate, just like I always do, I'm going to calculate the magnitudes first. So for E1, magnitude is equal to K. 1 times 10 to the -6 coulombs divided by 0.5 meters squared. That's E1. E3, well, it's along the diagonal, so it's K times 3 times 10 to the negative 6 coulombs divided by 2 times 0.5 meters squared. Okay. Because it's farther away, it's along the diagonal. Then E5 magnitude is equal to K, 5 times 10 to the negative 6 coulombs divided by 0.5 meters squared. Okay. Well, 1 and 5 are pretty simple in the sense that 1, there's no y component for 1, it's all in the x direction. For 5, it's all in the positive y direction. But for 3, you have negative x and negative y components. So finding the resultant is an exercise in adding vectors, just like we've been doing. You have the magnitudes, you have to find E1. I'll write it out real quickly. E1x is equal to E1. E1y is equal to 0. E5x is equal to 0. E5y is equal to E5. And E3x is equal to E3 with a negative cosine of 45 degrees. And E3y is equal to negative E3 sine 45. Okay. You see what I mean? Just add them up like we always do, vectors. Okay. They're summable. So we're going to find, I'll give you a preview of what we're going to do next time. Yeah?
You have E3 as negative because it's to the left and down.
Yeah. Yeah, the origin is here. I want to add these vectors and find the resultant. So this has a negative x component, and negative y component. Okay. This angle is 45 degrees. It's a square. Okay. All right. Now, this is the equation that I keep using. Okay, Q over R squared, R hat. So what we're going to do is we're going to use that idea to find, like I said a little while ago, we're going to find the electric field due to continuous distributions of charge. So what we'll do is we'll take these blobs of charge and we'll break them up into little bits of Q. So we'll have little delta Q's and we'll let delta take the limit as delta goes to 0. We'll do Riemann sums and have all kinds of fun. You need to lose your fear of Riemann. Okay, I'll see you guys next Wednesday. Or